Hi, my name is Terry Four. I'm the Director of Development with Num4j. Num4j is a nonprofit organization in the United States that supports open source scientific computing projects. We serve as the sponsor organization for about 36 different projects, and we provide a range of services and support to our sponsored and affiliated projects all throughout the year. We also cultivate a community of users and developers around our projects in a number of different ways, but most notably through our PyData community event series. And I'm here today to introduce Luanne Misquitta. Luanne is the VP of Engineering of GraphAware, and GraphAware is the world's #1 Neo4j solutions consultancy and has been working with Neo4j for over 10 years now. Luanne has been connected with Neo4j and been involved with them for a number of years and in many different ways. And today she is going to be presenting on Malt Aware, discovering what to drink with Neo4j. So without further ado, Luanne, welcome to Nodes 2020.
What better way to start this amazing event than with the perfect single malt? Good evening or good morning, everyone. I'm Luanne and I run engineering at GraphAware. We do all things graphs and Neo4j, and we're the creators of Fume, a graph-powered insight engine. You're going to hear 5 of us speaking today on topics ranging from graph visualizations to NLP and security. Right now, though, I'm going to be talking about recommendations with Neo4j. Recommendation engines have always been a popular use case for Neo4j, and I'm going to show you why that is and the different ways to produce good recommendations with very little effort. We will start with a data set of whiskies and go through a progression of recommendations such as content-based, collaborative, and some special ones to mix things up. Why even implement recommender systems? So recommendations are everywhere, like graphs. They show up when you shop, when you plan a holiday, social networks. Traditionally, recommender systems were a type of information filtering system used mostly in commercial applications to predict a rating or a preference that a user would give to an item. Now with the knowledge systems and inference engines, they blend together a bit to extend to fields such as finance, to find fraudulent transactions, to law enforcement, to find people of interest, and so on. The main challenges for a real-time recommendation system are: 1, to discover the items to recommend; 2, to pick the most relevant ones to present to the user; and 3, to find those relevant recommendations as quickly as possible. So what do these systems do? Because they try to predict how much a user will like or prefer a given item or target, they assist users in decision making. They also take into account business strategies, since ultimately the goal of recommendations is to increase business or retention rates and such. They don't just treat each user as interchangeable beings, but they try to personalize recommendations or take into account the context. And they do this by correlating different data angles to come up with and what they believe fits best for each unique user. And all this has to be done in a performant and a time-sensitive fashion, since recommendations calculated a day ago may already not be relevant at the current time. And they need to be explainable so that we can deduce how successful they are and tune them if they're not. Now, decades have passed since software systems that are now called recommender systems were first developed, but the field continues to grow and improve to provide more and more accurate recommendations. They aren't always easy, and some of them continue to amaze every single day with their very diverse recommendations. So no matter which way I try to reverse engineers these treatment for aquariums, which I have never dealt with nor shown any interest in at all, seems really very strange. And the wire baskets as well, in fact. But recommendations and graphs were made for each other, and today we will see why this is. Now, top selling items is no longer good enough. The "you may also like" is a modern way to offer tailor-made suggestions and provide very real-time targeted recommendations to potential consumers. The underlying technology has to support this. There's a buying history to capture and also analyze together with current choices or indicators. And then we match this all up to provide the best recommendations. And this has to be done fairly quickly before consumers, especially in today's digital and time-pressed world, begin to move on to another website. So graph databases give equal importance to storing both the data, which is customers, products, categories, etc., and the relationships between them. Who bought what, who likes what, which purchase happened first. It's a semantic rich model providing context in the form of named and directed relationships between nodes or entities. So we can represent users and the items that they've bought or indicated some interest in, the features of the users, their preferences, their tastes, demographics, and so much more in a graph, and traverse this graph really fast to derive some value from those relationships without incurring the high join cost when you model this data in rows and columns. Why do you receive or not receive the recommendations that you expect? Because we recommend items based on how they're connected, what features they have in common, what characteristics they share, tracing the reasons for the recommendation and hypothesizing about the various parts that cause the item to be recommended is significantly easier in a graph. Of course, there are some values that could be calculated, such as the similarity, but even in those cases, based on the input to the similarity algorithms or calculations, we have a fair idea into why it is the way it is. And in fact, this is exactly how I tuned some of the queries or the calculations for the graph that we're going to see today. Apart from this, graph models are self-explanatory. They are easy to understand by non-technical users, and they're very easily visualized. So overall, graph-based recommendations are easier to explain than black box statistical approaches. Neo4j is a schema-free database. Without the rigid structure of SQL databases, which make schema changes hard and mostly scary in production, with Neo4j, it's easy to not only add properties or types of nodes or relationships, but also to refactor the schema fairly easily. Plus, it's also possible to have the old and the refactored models coexist till all dependent applications can migrate. Neo4j is often used as a storage layer that connects data from multiple silos, and having quick access to everything you know about a user or a product allows you to make more relevant recommendations. Recommender systems typically need to analyze a large amount of data to produce meaningful results. So Neo4j's native graph engine uses index-free adjacency to eliminate the need for these complex joins and enable real-time traversals. So for today, here are the concepts that we're going to visit. We're going to talk about personalized recommendations, because recommendations that aren't personalized aren't very useful at all. So different recommendations for different users based on taste. Now, since we speak of personalized recommendations, the system needs to know as much as possible about users and items, and this typically takes the form of a set of features or characteristics of an item or the preferences and behaviors of the user. And these are commonly known as user or item profiles or user or item models. Now, how these models get built range from very simple, as we will see today, to those built out of sophisticated learning algorithms. And the features can be collected implicitly or explicitly. So for example, we derive some characteristics of users by analyzing the whiskies they rated highly. This is implicit collection. We also asked a subset of users to indicate their favorite flavors, and this is explicit. Now, with collaborative approaches, the central idea is to use information about the past behavior or the opinions of an existing user community to predict which items the current user will be interested in. This method suffers from the assumptions that if users had similar tastes in the past, then they will have similar tastes in the future, and that their preferences remain stable over time. But we'll see some ways to get around that today. And finally, context. Context is very important. And this ranges from things like who you're with, who you are maybe purchasing things for, location, time, seasons, all these sorts of things. Right, so here's the graph model that we are going to use today. At the center, you see the most important entity or node, which is the whiskey. And we have a couple of descriptive nodes surrounding it. So we've extracted the flavors. So the taste profile, you may say, of the whiskey. For quite a few of them, we know which region they come from. For a smaller set, we know what cask they were aged in, because cask is quite important. We know the bottler, not so important. And we, at least with the data we have, and we have a set of people, users, that have actually reviewed these whiskies, and they've provided a rating on the scale of 1 to 5. So that rating, in fact, is stored as a property on the reviewed relationship, and the reviewers will represent all our users today. So it's a small data set, but nice enough to explore and test out our hypothesis. And we're going to start from the beginning. So we're going to onboard some users. We are going to start recommending some whiskies, and we're going to improve as we go along. So the cold start problem. Now, this is quite typical of collaborative systems where users, they don't have enough history, or there are just too few users to be able to use the opinion of the broader community. And in fact, that's the very case with our graph today. Now, this can also apply to new users which haven't been reviewed yet. So in collaborative system, if new items haven't been reviewed yet, they would just fail to be recommended, because they would not be picked up. Now, this can be quite a serious problem, because it can result in the loss of new users who stop using the system due to inaccurate recommendations. And in fact, their own lack of history is like a perverse contributor to this whole phenomenon. So instead of providing subpar recommendations based on insufficient ratings in the system, let's just have the system not use a collaborative approach till the distribution of users and their ratings crosses a certain threshold. So different domains attempt to tackle this in different ways. And in our case, we are going to start off by recommending whiskies that the general population seems to like. On our whiskies today, we have a couple of external indicators in the form of a category. So these are pre-categorized. And they're categories like smoky whiskies, or the floral ones, or the fruity ones. So what we're going to do is present generally liked whiskies across these categories, and this should be a good enough variety, and we hope that there's something in there for everyone. So here's our initial recommender query, right? We'll walk through it. It's pretty simple. We find all whiskies that have at least 2 reviews. Now remember, our user base is fairly small, and we are onboarding new users into this graph. So we don't want to do collaborative recommendations, because they are likely to be fairly inaccurate. So all whiskies that have at least 2 reviews, okay? We are going to check what rating they have. So the average rating, we want to make sure that they have at least a rating of 3. We don't want to rate whiskies that nobody really likes. And we're also going to make sure that the general population of reviewers sort of agree on the rating. So there isn't too much deviation in those ratings. We will pick 3 from every category. So we have like a nice mix, and that's what we present. So here you see these are the whiskies that we're going to just recommend to brand new users who try to use our system. Now the little colored badges on those whiskies represent actually the category. So for example, the blue ones are the smoky whiskies, typically with a lot of sea flavor, so a lot of brine in them. The pink ones are fresh fruit with a lot of vanilla. The black are the richly peated ones. Yellow, heavy on the malt and the honey, etc. Right? So we took this initial set of whiskies and we ran it across our test users, and we actually found that every single user found at least 2 to 3 whiskies that he or she had tried before, mostly liked, and one or two dislikes, right? So we see over here there are 3 users, and all of them have found a whiskey that they've tried before or that they might want to try. So not a bad way to start recommending whiskies, right? We haven't put off users from from staying on our site already. So now let's move ahead to content-based recommendations. So these lean more towards the information filtering technique, and it's based on the profile of user preferences matching with item characteristics. So now in some cases, the item features are manually created. So for example, every whiskey can arrive with a tasting profile from the distillery indicating characteristics such as smokiness or sweetness and whether it's chill filtered or not. And having this provided uniformly is usually feasible only in smaller systems that deal with mostly like a single source of curated data. So then we have the features that can be extracted, typically from text such as descriptions or reviews, or from metadata, or from catalogs, for example, that the distiller produces, the region, the type of cask. So for users, their preferences can either be indicated explicitly or inferred from their behavior. We are creating a content-based user profile or model based on a weighted vector of item features. And today we're going to go very, very simple, just to show you that you can start building recommendations quite easily from even basic graphs and then add on the complexity as you go. So the advantages of this method is that it doesn't actually rely on the existence of a large user set. And because the characteristics of the items are used and not their ratings by previous users, new items can be recommended almost immediately. And this is why content-based recommendations are potential other solutions to the cold start problems. However, this method does have its disadvantages. It definitely requires some domain knowledge to produce a good model, and it is constrained to making recommendations based on the existing interests of users. So it tends to not actually venture into new territories. So generally, whiskey drinkers tend to favor certain flavors. So in our graph, we've extracted the flavors of whiskeys from the content of the description and the reviews. And we can now easily see how the flavors related to these whiskeys also serve to paint a picture of our users without them having to explicitly state their preferences. So this particular subgraph shows our user with whiskeys that he has rated highly. So we see Franta with the brine and the smoke, typical characteristics of the Isla whiskies, and he favors the toffee notes as well. And a different profile, this time mine, leaning heavily towards the peated whiskies. You see the smoke in the center of it all, brine, some fruit. And we begin to see that some whiskeys are close to each other in terms of flavor profiles. So as I said, the colored badges indicate some of the data that we already have around their categorizations. But even without the blue ones indicating the seaside smoky whiskeys or the black ones indicating the richly peated ones, we can see quite clearly that their flavors alone tend to bring them together. So we are going to use the flavor profile of whiskeys to calculate how similar they are to one another. Then we will use the ratings of our user to find the whiskeys that he or she liked, traverse through to similar whiskeys and recommend those. To calculate the similarity score, we will use an algorithm from Neo4j's graph data science library, so the node similarity. This algorithm compares a set of nodes based on the nodes they are connected to. And this fits quite nicely with our flavors. So two whiskeys will be considered similar if they share neighboring flavors. Now this particular one computes similarity based on the Jacquard score. So A and B are two disjoint sets, and we are looking for the overlap over the total set. So essentially we need a bipartite graph. Now on our small graph, this algorithm runs very, very, very quickly in seconds. But you should note that the complexity grows quadratically with the number of nodes to compare. And this is very good to keep in mind. There are many algorithms out there that you can use, but you should be conscious of their computational and memory requirements, the size of your data, so that you can pick the most suitable one. Now the graph algorithms run over a model which is typically a projection of nodes, relationships, and properties from the underlying graph. And they are stored in memory using compressed data structures which are optimized for topology and property lookups. The graph catalog is basically where all the graph projections are managed in the graph data science library. Now, before we can use the node similarity algorithm, we need to create a projection of the graph that we wanted to operate on. And this is a bipartite graph. So just to refresh our memory, a bipartite graph is a graph whose vertices or nodes can be divided into two disjoint and independent sets. So here we see whiskey and flavor, and every edge or relationships connects a node from the whiskey set to a node in the flavor set. Now here we are doing a native projection for our named projection called flavors, and we are projecting only the whiskey and the flavor nodes along with the flavor relationship type. Then we call the node similarity algorithm and we tell it to operate on our named graph called flavors. We're using two config properties. The first is degree cutoff, and this is the minimum degree of the node to be considered for similarity calculations. So here we are actually just avoiding all whiskeys that have a single flavor. Then we have a similarity cutoff of 0.3. So we actually aren't storing similarities with a value less than 0.3. We're not interested in recommending those at all. So now this algorithm returns pairs of nodes with their calculated similarity score. We're going to write this data to the graph in the form of a similar flavor relationship, and we're going to store the similarity score as a property on this relationship. And it really helps to materialize these calculated similarities in the graph for easy, more performant queries later, and especially when calculating similarity on demand can be quite expensive. So you will see on the right there, the shape of the similarity graph. That's really a visualization of all the whiskey nodes and the similar relationship between them. So I'm going to zoom in here a bit to two of those pairs calculated to be exactly similar. So a score of 1. So we can see quite clearly here that they share an entire set of flavors. And so the score actually makes sense. Now we've got to keep in mind that we calculated similarity purely on the basis of the flavor nodes. And that's what this algorithm has given us. It does not take into account other characteristics of whiskey, such as whether they're similarly rich or dry or sweet. And for this, we'll use another way of calculating similarities a bit later. So now that we have the similarities, we can use it to recommend whiskies. We are going to start at our target user called P. If he or she is a person in the graph with the label reviewer. We want to find all the whiskies that he or she has reviewed with a rating of more than 3. Then we're going to look for other whiskies which are similar to those. Make sure that he hasn't reviewed them before. Make sure that the similarity score is at least 0.4. And then we're going to order them more similar first, cut it off at 5. And we're going to write a recommended to relationship between the person and the whiskey and capture the date on which we recommended it and also the reason, which is flavor similarity, because later we're going to see different types of recommendations and we would like to know which recommendation came out of which algorithm. So for Fronter, the recommendations produced by the flavor similarity show some of the peated ones, some of the smoky ones, some of the floral ones, and I know thanks to Fronter that he actually does like 1 or 2 of these, so not bad at all. Why were they recommended? So this is our explainability concept, right? We want to be able to go back and say why we recommended this whiskey. So if we actually go and expand the recommended whiskeys, we will find that they have the similar flavor to the whiskeys that Fronter reviewed and rated quite highly, so 3 and above. So you can go back and just look at it, and it makes a lot of sense, right? And then we can go one level deeper and say, okay, so did the Talisker 18-year-old actually have anything in common with the Lagavulin 16? And you look at it and you see that yes, they did. They did have the orange and the brine in common, and from the other side you see the toffee and the honey in common, right? And that's what we wanted to achieve with the flavor overlap. Right. Okay. So let's switch a bit and try something else. So we're going to look at collaborative recommendations now. So the basic premise of collaborative systems is that if users have shared the same interests in the past, so they've rated the same whiskeys, for example, then they will have similar tastes in the future. So if two users have had their whiskey preferences heavily overlap in the past, if one of them buys and likes a new whiskey, the system will recommend it to the other and predict that he or she will also like it. Now, user-based approaches can be significantly challenging when used on very large graphs. So when we're looking at tens of millions of users and items, and the feasibility of computing these predictions in real time decreases. Specific user preferences are also not taken into account. So in the example you'll see next, we would actually miss out on cases where it's more significant when two users agree on a controversial choice because we want to actually amplify this prediction. Or the users that rate whiskeys in a particular way because there's a characteristic of that whiskey that's important to them, but it's not the reason for other users rating it similarly. So that's why this method essentially can be used in systems where item features are not readily available because they don't depend on the features of the items. Now, finally, the prediction quality can be low when the data is sparse. So when there's not enough ratings, for example, the quality can be low. But when there is sufficient data, then it can actually help users discover new interests. This is a bit different from the content-based. Okay, so for collaborative recommendations, we are looking at the user item matrix, right? So given user item ratings and an active user, we want to identify other users that have similar preferences to those of the active user in the past. And remember that this assumes that user preferences remain stable over time. Now, item-based also predict how users will like or dislike items because of the similarity between the items and not the similarity between the users. But both of these are graph analysis problems, making use of paths found between items and users. Now, here's our user item matrix. So we see a couple of users in there. We have Pavel, myself, Michael, Vince, couple of whiskeys that we all rated. And even without doing further calculation, it looks fairly clear that Pavel should be recommended the Kalila 12, right? We can see that all three of us rated, he hasn't tried it yet. So it seems logical that we should recommend this to him, and there are high chances that, he would drink it with one of us anyways. So to calculate, how do we calculate this? So how similar are users in their reviews, right? We are going to use Pearson correlation here. Now, as I said earlier, there are quite a few algorithms to choose from, but understanding the shape of your data and what the algorithm focuses on is useful to know which one to try. So analysis has shown that Pearson correlation outperforms some other methods of comparing users. And that's what we're going to use today. So this is opposed to like cosine similarity being better for items. There are also other ways of calculating similarity. So in some cases, the adjusted cosine similarity can do as well as Pearson. So again, I encourage you to experiment and pick what suits your domain best. So in our query over here, we again start with the same premise. We want to find people that have reviewed at least 2 whiskeys, right? So that's the minimum criteria. We want to find all the whiskeys they've reviewed, and then we want to create the equivalent of the user item matrix over here, but this time in the form of a vector that we can provide to the algorithm, right? So you see that we collect the ratings for reviewers, so for users and their whiskeys. Then we collect them all so that we have the global data set, and we supply it to the Pearson correlation algorithm. That's our data. Again, we have a similarity cutoff of 0.3. What we get back is the 2 items and their similarity. And similar to before, we simply write this to the graph. This time we are writing a similar user relationship between both the users. Okay, so this helps us say which users have similar tastes. And now that we can find similar users, we are going to write our recommendation query, our second recommendation query, or a third one actually, to recommend items to other users. So we start with our target to user, called user in this query, matching the ID. We find all users similar to that particular user. We find all whiskeys that they've rated with at least a rating of 3. And we make sure that the user hasn't already reviewed that whiskey. We order it, we limit it, and we create our recommended relationship. And as you see on the right, indeed, as we imagined, the Kalila 12 was indeed recommended to Pavel. So I guess, Pavel, that's a sign that you should be drinking this whiskey. Right, so we've seen this form of item similarity, user similarity. Before we saw the item similarity where we used only the flavors of each whiskey to calculate node similarity. But you know, this isn't enough for us. There are other nuances of whiskey that are very important when predicting a rating, such as the cask, which imparts a lot of flavor, the sweetness, the richness, the smokiness of the whiskey, or even the region that produced it. Now, for this, we can use node embeddings to compute vector representations of the nodes, and specifically, we will use node-to-vec for this today. This is based on random walks in the graph. Now, what does this particular node-to-vec algorithm accept? So again, we are projecting various dimensions of our graph for this algorithm to operate on. So we are projecting all the nodes that we're interested in. So the cask, the whiskey itself, we're gonna add the flavor back into it, but we're going to add other characteristics such as the body, the richness, the smoke, the sweetness. These are all values that we've extracted, and they run on a scale of 0 to 5, 0 being not smoky, not rich, not sweet, all the way up to 5. Whether it's chill filtered or not, the category. And then we're going to project each of these relationships. So we know that from the whiskey to the flavor, we have a flavor relationship. From the whiskey to the cask, we have an aged in cask, and so on and so forth. So these are the nodes and relationships that we are going to project and supply to our node-to-vec algorithm. And we're going to instruct it to do 10 iterations of the whole thing, do a walk length of about 10. And these are parameters that you will end up playing with to see how best you can get a good vector. And then we're going to write these embeddings as a property on our whiskey nodes. And the property is going to be called embedding node-to-vec and T1. So this is our first version, right? So once we run this, if we inspect our graph, we will see a vector, so an array of numbers which represent the embeddings produced by this particular set of characteristics we chose for our graph. Now, pretty much the same as when we calculated the similarity between the users. Here, we're going to use the vectors produced by the node-to-vec as input to cosine similarity in the graph data science library. So we get a score and we create the similar item relationship between both the whiskeys, right? So again, we match all whiskeys in the graph, we calculate cosine similarity, and then we merge in a similar item. And now that we have this, we can simply use this as we did before. So we can find the highly rated items, and then we can find the items similar to those, make sure that the user hasn't already reviewed them or tried them, and send them back, right? So an example of what that query produced for me earlier is it found these two items to be, it found them to be actually very similar. And we see here that they definitely share 3 of the flavors. And remember, we projected the flavors. We wanted them included in our embeddings. And if you have a look at the properties and the panels on the right, so you also see that they share common or close values in terms of their richness and their smoke and the body, etc. Right? So yeah, fairly similar. But then on the other hand, we find this pair, which was also similar, right? So we have these two whiskies here, and the only thing they have in common was the sherry finish cask. So, so these are some of the caveats of the embeddings, especially because the graph that we're operating on isn't very connected, and because Node2Vec works on walking the graph. If you have mostly a disconnected graph, you could end up with things like this. And this is why it's really, really important to understand the characteristics of, or the shape of your graph itself and the underlying algorithm, and match them up, try them up, to make sure that you don't overlook things like this, right? Okay, so these fall into like our standard categories of content-based and collaborative recommendations, right? But these are not the only two avenues you have for recommendations. So how about some personalization? So we find quite commonly, at least in whiskey drinkers, that there are people quite a lot of people that fall into the category of liking a lot of smoke or no smoke, right? And they don't like the whiskeys with very little smoke. It kind of just underwhelms them. So these are personas that you can find in your data set. You can calculate this and you can mark these people with a property or a label. And then you can have special recommendations for personas like these. So in this case, we're going to recommend different whiskeys for people that lean towards the heavily smoked category, right? And they wouldn't like anything lightly smoked. But we have similar flavors, right? So here we're trying to broaden the horizon of what people might like to drink. So they're not completely out there, but they share flavors, but we just dial down the smoke all the way to zero and suggest these whiskeys to other users, right? So we see in this particular graph that the whiskeys that have been recommended here share the flavor profile, but no smoke. And we actually find this in Franta's graph, for example, where he has a good balance of very smoky whiskeys and then not smoky whiskeys, right? And then you have people that like, the middle ground. So they shy away from anything without smoke, and they shy away from very heavily smoked whiskeys. And here again, once we are able to identify these sorts of people, then we're able to tune our recommendations for them. So apart from all the previous kinds of recommendations that we could give them, there are some of these that we want to insert into their recommendation list to provide them with something new to try. So here we see very similar queries, right? So all recommendation queries, once you've calculated similarities and scores, they're just a matter of figuring out different paths you can traverse or different parameters that you can dial up or down. So we're using a similar flavor, and we're making sure that the smoke is definitely under 4, right? So the mid-range smoke. And our subject for this particular experiment was Sunny, and we know for a fact that this is the profile he falls into, and the whiskeys that we recommended to him are actually the ones that he likes. So pretty good and pretty neat. Then we have other kinds of factors, right? So tastes, they change or they evolve over time. Now, the drawback of the previous methods is that they assume that the tastes or preferences remain stable. Let's look at this example. So we are looking at Aldrin over here, and we read from left to right. So this is the order in which he rated whiskeys over time. So reminder that the ones with the blue badge were the smoky C flavors, right? So they start very, very clearly in the smoky range. But then over time, you see the pink ones that show sort of a graduation towards no smoke. They move towards the delicate and the floral kinds of whiskeys. So we want to take this into account. We don't want to ignore the fact that perhaps taste is changing, and we want to start making guesses into, is the user's taste really changing? Maybe we need to recommend more like what he drinks currently rather than stick to, what he drank in the past and maybe isn't interested in drinking so much nowadays. So if we wrote our, what I would call our standard normal recommendation query, right? So we match the reviewer, in this case, Aldrin, all the whiskeys that we reviewed before. We go through our similar flavor relationship type. We find ones that match it and we return them back. So this is like a mix of smoky, non-smoky, rich, delicate whiskeys, all of them in one, they don't take into account time. But now we can change this query a bit, so we can weight it by time and now detect that potential switch or that progression of taste into more floral ones. And we start to surface these slightly more floral whiskeys at the top of our recommendation. And we measure to see if the user is actually interested in them, or was this like a one-off, right? So taking into account changing taste over time, I think is quite important and keeps the user engaged. Then we have serendipity, right? So the accuracy and recommender system. So when you start out, accuracy is important, or the irrelevance of the recommendations just drive people away. But then it begins to get boring. So would you like to listen to music from your favorite artist all the time? Would you like to drink more of the same whiskey? So probably not. We like to be surprised in pleasant ways and discover and appreciate something new, so something that we didn't set out to find. And this is very important in recommender systems as well. It keeps customers interested. It makes business sense as well, right? To offer diverse recommendations, potentially sell into new avenues. It is hard to measure. So serendipity can be introduced into in many different ways, and it differs completely from domain to domain. You might want to recommend across a wide range of choices. You might want to recommend something new, something unexpected, but still with some thread of connection to the user so that they're completely not out there, like the aquarium cleaners. So earlier we calculated similarities between whiskeys based on flavor. Now we can project a graph containing those similarities and supply to the Luanne similar community detection algorithm. So this Luanne method is the algorithm to detect communities and large networks, and it evaluates how much more densely connected the nodes within the community are compared to how connected they would be in a random network. So we calculate this community and we write that number as a property called the Luanne flavor on the whiskey nodes. And when we actually visualize this, this is, for example, one of the communities which has similar kinds of whiskeys. So what can we do, right, to introduce this level of surprise or something you didn't expect? From time to time, we might actually recommend a whiskey from a region that the user hasn't tried before. It won't be completely out of the blue because we will do it from communities that contain whiskeys that he or she likes. So by now you're very familiar with this sort of query where we find users, we find the whiskeys that they really rate highly, but now we're actually going to pick other whiskeys from the same community as those, and we are going to we're going to filter out whiskeys from a region that the user has tried before. So what this shows us is that Michael actually has plenty of whiskeys to try from different regions here, like Highland or Speyside. Always recommending things that best fit into the user's current neighborhood in terms of similarity can quickly hit this problem of redundancy, because you'll have the same items recommended over and over again with very little variation. Now, in some cases, it might be best to boost these weak ties. So recommending such a new item, which if it were accepted, would create a bridge between these strongly connected subgraphs. And they can enable recommendation algorithms to actually start to reach the unexplored parts of the graph. So this also provides an element of serendipity, allowing users to explore new things. And this is, as you see in the link on the previous slide, this is from our blog written by Miro, and he calls it the not recommendation. So this query finds whiskeys with similar flavors to the ones liked by Tony, but then it filters out those that have been reviewed by any other reviewer who's similar to Tony. It also excludes any whiskies that were reviewed by people that reviewed the same whiskies as Tony. So this kind of breaks out of Tony's circle and perhaps brings in something novel from weekly related networks. So finally, we need to put this all together into a recommender system. So we have in this diagram the items analyzer, which processes features of the item and results in an item profile that is persisted in permanent storage. User profiles are built similarly with explicit or implicit input. The recommendation engine uses these models to produce the list of recommendations, and this itself uses many different recommenders. So essentially, we're always looking for a hybrid system that uses the best of content, collaborative, context-sensitive recommenders, as well as all the things that come with recommendation engines, so filters, blacklists, score boosters. And finally, the loop is closed by taking into account user feedback to constantly evaluate the effectiveness, tune, and improve the recommendations. So graph-based approaches shine, as we've seen today. User item data sets can be easily represented as bipartite graphs, and the same graph model was used to extract different vector representations of users and items. Pathfinding was very efficient. So I hope this gives you a taste of all the dimensions you can use while recommending items using graphs. And this is really just the beginning. There are plenty of interesting queries to try, algorithms to explore, theories to test, but best of all, getting started to produce recommendations with a graph is really so easy. And before I end, I have to say special thanks to all my whiskey-loving GraphAware friends and friends of friends who patiently rated whiskeys for me, tried out the recommendations, filled out many forms. And of course, it's been really my privilege to be able to consult our chief scientist, Alessandro, read his book, The Graph-Powered Machine Learning, and he provided advice on all the embeddings that you saw in the slides earlier in my presentation. So thank you, Chief. And with that, that is the end of my talk. I hope you enjoyed it. So we probably have just a couple of minutes for some questions. I'll pick one of them. So what would you say is the minimum we should know or we should have to begin recommendation? So a bit of a broad question, but I would say that understanding your domain and your users. So what makes for a good recommendation? How do you measure whether the recommendations are any good at all? What's the volume of data and users? Because this impacts which algorithms you pick, your overall architecture. Do you need to pre-compute some aspects? Can you react in real time to events that change the course of recommendations? So typical cases, right, where users blacklist suppliers and you want to recommend really, really quickly and not recommend that supplier in the next 5 minutes. Do you have some objective measure of quality? Are you able to use feedback loops to train, improve the engine? And also the ability to look at why items were recommended. So for example, I found today a few pairs of items which had just one feature each, and that feature was shared. So we want to make these sorts of pairs, less prominent, less important. And without you inspecting your domain and your data, you could be surfacing a lot of recommendations that really aren't very good. So yeah, I would say those would be the top things to keep in mind before you go off and build a recommendation engine. Is that a custom visualization tool in your screenshots? In fact, those are knowledge graph visualizations from our product Hume, which I spoke about earlier, and we're almost out of time, but you can visit our website, graphaware.com, or just contact us to learn more about it. Thank you. Thanks very much. And enjoy the rest of the event today.